Stanford University.
The last time, as I remember, and I have a poor memory, so correct me if I'm wrong, we talked about magnets, and did we talk about phase transitions and mean field approximation? And I showed you how the phase transition between a magnetized, how the phase transition happens to a magnetic system, a simple magnetic system, the magnetic system being the system on a lattice where every spin is coupled to its nearest neighbor by a term in the energy which seeks to align them. In other words, the energy is lowest when the neighboring spins are aligned. The ground state of that, the lowest energy state, and which describes zero temperature, is all spins perfectly aligned. As you begin to heat it up a little bit, the spins begin to jiggle a little bit, but any spin still has a bunch of neighbors around it, and particularly if the dimension of the system is very high, and actually for our purposes 3 dimensions is pretty high, then the number of bonds connecting that spin to its neighbors are also high. And so I showed you how to use the mean field approximation to calculate. Mean field approximation simply means postulate an average for all the spins, and in particular in this case it means all the spins neighboring to our target spin, to the spin that we are going to focus on. And just imagine that they are frozen at their average value. These spins are frozen at their average value. That gives you an expression for the energy of the one spin that is left over, the one at the center. And in a sense, the other spins surrounding it give it a bias to point in the same direction as the average spin of the others. The higher the dimensionality, the more neighboring spins there are, the better the approximation of saying you can average over them. But that's the basic idea of the mean field approximation. And then let me remind you what you do. You calculate in the background of the other spins, you calculate the partition function for the one extra spin. You then calculate the average magnetization of the extra spin. In other words, you calculate the average value of sigma of the extra spin there. What was it equal to? Anybody remember the formula for it? I don't remember the formula for it. I just want to go back and...
Minus the average energy over 2SD?
No, but there was a formula with a tangent, a hyperbolic tangent.
Yeah. Hyperbolic tangent 2 beta SD.
Hyperbolic tangent of?
2 beta SD.
2 beta SD. D is the dimensionality of space, and it simply represents the number of nearest neighbors to this fellow over here. All right. Beta is the inverse temperature. Where did the 2 come from? Oh, I remember where the 2 came from. Yeah, because the number of nearest neighbors is twice the dimensionality. And S was the average spin at the average spin of the entire ensemble of spins. And then the consistency requires that this be the same as S. In other words, this spin is no different than all the others. I said that all the others have an average spin S, and we get a consistency equation. S is equal to tanh 2 beta S times D. And if we can solve that equation, then we will determine what the average magnetization is as a function of the other variables in the problem, beta, D, and so forth. All right, so let me just remind you what that looked like. We plot S. S is just a linear function. S of what? S of S. All right, we plot S of S is just a straight line, S equals S. And then we superimpose on that the graph of tanh twice beta SD, and that looks something like this. Let's see, if the temperature is high, when the temperature is high, that means that beta is small, then the tanh function looks like this. It's very flat. It asymptotes to 1. It's linear at the origin here, but the slope is less than the slope of this straight line over here. And so there's no intersection of this blue curve with a black curve other than the origin. And that means the only solution to this problem is that S equals 0. Now we start decreasing the temperature. That means increasing beta. And we discover that this curve moves in. And eventually, its slope at the origin will become equal to 1. When you go beyond that, the curve will look like this. And you have two new solutions. These two solutions are, in fact, the stable solutions. It's possible to prove that this solution over here really is unstable, that if you try to make the magnet behave as this solution tells you, any tiny little perturbation will, in other words, over here, what does it say? It says that the magnetization is 0. How do you make the magnetization equal 0 if it doesn't want to be 0, if it wants to all line up? Well, you simply take the two possibilities all lined up one way plus all lined up the other way. In other words, you make a probability a half that they're all lined up in one way, probability a half that they're all lined up in the other way, and sure enough, there will be a solution which will correspond to no magnetization. But that's a highly unstable situation. Any small, stray, very, very tiny magnetic field pointing either up or down will tend to flip the magnets to the preferred, in the preferred direction, and you will either get this or this, depending on which way the, well, two possibilities. You'll either get this or this, depending on the direction of that extremely weak magnetic field. Now, I have not included that very weak magnetic field in the calculation. We could, but that's just a nuisance. We simply know that if we have a lot of spins and they all want to line up and they're reinforcing each other, binding each other to be in the same direction, that at low temperatures they will tend to line up, and either they will line up positively or negatively. S will either be positive or negative, depending on nothing more than the value of, let's say, an infinitesimally small background field, which is of such insignificance that we don't even need to worry about it in the dynamics of the magnet. Okay. There's a critical point. The critical temperature is the temperature, or the beta over here, which makes the blue curve have the same slope as the black curve. In other words, it's the first point, it's the point at which you're just on the cusp of having spontaneous magnetization. I didn't draw that well over here. I meant it to be tangent to the black curve. So as I vary beta, I eventually hit a point where the blue curve is tangent to the black curve. There's only one solution at that point. The magnetization is 0, but then when I just go epsilon past that, just a tiny bit past that, then the magnetization, the spontaneous magnetization happens, and that point is the critical point. All right, it's the critical point, and it's the point where tanh has unit slope. So what does that mean? What's the slope of this tanh here at the origin? It's the derivative of tanh with respect to S. So what's the derivative of tanh with respect to S? at the origin. I think it's just twice beta d. So when twice beta d, is that right? I mean, if we differentiate tanh, can anybody do that? All right, let's do it. Let's do it just to convince ourselves that I'm right. What is tanh? Tanh is sinh over cosh, right? Sinh over cosh. So sinh, that's right, just sinh x over cosh x. We'll differentiate first with respect to x, and then we'll differentiate x with respect to the argument of the tanh, right? Just usual rule for calculating derivatives. The derivative of sinh is cosh, right? So let's do, what's the usual rule? Denominator times the derivative of the numerator. Derivative of this with respect to x is equal to the denominator cosh x times the derivative of the numerator. Derivative of the numerator is also cosh x, cosh squared x, minus the numerator times the derivative of the denominator. So I think that should be minus sinh squared x, plus or minus. We'll see in a minute. Let's see. We have numerator, sorry, we have denominator times the derivative of the numerator minus numerator times the derivative of the denominator. So it looks to me like cosh squared minus sinh squared. Derivative of cosh is equal to sinh, and derivative of sinh is equal to cosh.
As numerator is 1.
The numerator is 1 at x equals 0. The numerator is 1? Oh, cosh squared, yeah. Cosh squared minus x sinh squared is 1, and this is just equal to 1 over cosh of x squared. Okay, so, and that at x equals 0, right at this point over here, at x equals 0, that's 1. Cosh of 0 is 1, so this is all equal to the number 1. That's the derivative of the tanh with respect to the argument here, but then we have to differentiate the argument with respect to s, and that will give us a 2 beta d. So that's where the 2 beta d comes from. The derivative of this with respect to s at the origin is 2 beta d. And when that becomes equal to 1, in other words, when the derivative of this curve just matches, just kisses the 45-degree line here, that's the critical point, or that determines the critical temperature. And so the critical temperature, let's see, did I miss a J out of this? Wasn't there a parameter J that,
Yeah,
yeah.
use that as a temperature, or as 1 over beta.
Yeah, it's there. There's a J there, a J. All right, so this is 1 over temperature here. And if I shift it to the other side of the equation, it just gives me the critical temperature at which the T critical is twice D times J. Notice, among other things, that the critical temperature gets higher with increasing dimensionality. Why is that? Well, low temperature, you're in the magnetized phase. The question is, how long or how high can you heat it before the temperature thermal fluctuations disrupt the magnetized phase? And the answer is the more neighbors that you have, the higher the temperature you can get to before you'll escape from their tendency to hold you in place. So that's why the critical temperature increases with D. You get to higher temperatures before the magnetization disappears in higher D. It's proportional to J. J was just the strength of the coupling between neighboring spins. The stronger the coupling between neighboring spins also increases the temperature, and the two came from someplace. All right, so now if we go back, I know I explained this, but let's do it again. if we go back to the phase diagram, let's go back to the phase diagram. And the phase diagram is a diagram which on the horizontal axis is just the temperature, and the vertical axis is the external magnetic field, which may be up or down. It plays the role in the magnet of the chemical potential in the fluid. All right, so let's put vertically here H. And if H is less than 0, in other words, the magnetic field is pointing down, it will bias all of the spins down, and throughout this entire quadrant here, the average spin will be down, that's for sure. But if you approach this line where H is equal to 0, it may or may not be that when you just get to that line, the magnetization is still there, or it may be absent. Okay? If it's there, that means there's a jump discontinuity, because certainly if you approach from the other side, you'll find that the magnetization is positive on this side, negative on this side, and if there's anything left of it right at the edge of this line here, it will have to jump. And that's a first-order phase transition. It's called a first-order phase transition. It is the sort of thing that happens as you increase the density of a gas. The chemical potential can be used to increase the density of the gas. You increase the density of the gas at fixed temperature, and eventually you will go from gas to liquid. All right? When does that happen? Well, it happens when the molecules get good and close together so that they're almost butting up against each other. Not quite. If they're butting up against each other too much, of course, what will happen is it'll freeze into a crystal lattice. But somewhere in between freezing in a crystal lattice and high temperature boiling water, somewhere in between, you'll have a jump in the density. Okay, or a jump in the magnetization. If you go to too high a temperature, this is T critical. As we've seen, if you go to too high a temperature, then the spontaneous magnetization disappears over here. And so the phase diagram contains spontaneous magnetization over here, and it disappears over here. As I said, you can go, I'm sure I did say this, but I need to remind myself as well as you. I can go from, let's call it the downward magnetized phase over here, which is also the gas phase. Let's call it the gas or magnetization negative. Over here, liquid, magnetization greater than 0. You can go across this boundary, in which case you see a sudden jump. And there's no doubt in that case that, that you've made a jump in the density. Or you can go around here and pass from gas to liquid without a discontinuity. So if you go around the critical temperature of water, or around in this way, you increasing the density, you can avoid the sudden jump. Yeah.
In the case, let's say you're going from the bottom to the top through the critical to the left, the lower arrow, does that imply that you're changing the magnetic field at one point?
No. All over. All over.
Okay.
Right. Right. What we're doing is we're changing the chemical potential. Changing the chemical potential is a trick for changing the density. All right, that's all it is. It's a trick for changing the density. If you like, you can simply think of yourself as squeezing the water, keeping the temperature fixed. We don't even really have to keep the temperature fixed. In fact, here I didn't keep the temperature fixed. It wandered from here to here. But if we wanted to have a precise version of it, we might cross at a fixed temperature. So in that case, you would be increasing the pressure, at the same time increasing the density, but keeping the what did I say? Increase the pressure, increase the density, but keep the system in thermal equilibrium with its environment so that the temperature stays the same, at some point the system will jump from gas to from vapor to liquid. All right, so that's the basic physics of the very simplest kind of phase transition.
So what do you see if you go around the outside? I can understand that if you
you go
compress
from where?
if you go around the outside to the right,
You go around this way.
yeah, if you go the other way, you see it go from gas to liquid. That makes sense. But on the top it's liquid, and the bottom it's gas. So what do you see if you go around?
You just see gas continuously change into liquid. The density increases. At no point do you see a sharp discontinuity between liquid and gas. The lesson is there is no sharp discontinuity. There is no infinitely sharp way to say this is a gas and this is a liquid. You can go continuously from one to the other without an abrupt change. Now, this is not true for going to a solid. The solid-liquid phase transition has a different character. What happens when you go from liquid to ice, let's say? What happens when you go from liquid to ice? You know, both the
You get a fog basically if you went around.
yeah, you get a kind of fog with a fog which gets denser and denser and denser, and then just becomes basically.
So are you saying that if both in liquid and solid state, like 5% liquid, 95% solid, I mean liquid and gas?
There would be no way to go from the liquid and gas continuously. There's always an abrupt change from solid to liquid.
Right. I meant gas to liquid.
Gas to liquid. Yeah.
So when you go around, you basically got like a fog of 5% liquid.
Yeah. Right. There's little droplets in it. You start down here, and it's mostly gas, but there are little droplets. Little droplets are part of the gaseous phase, having little droplets. If you look at it through a microscope, you'll find little droplets in it. Okay? But the little droplets come and go. What happens to them? They form and they evaporate. They form and they evaporate. They form and they evaporate. Likewise, up here, sort of symmetrically, the liquid will sometimes form little bubbles of gas. There'll be little bubbles of gas, but the little bubbles of gas will also, they won't evaporate, but the liquid will squeeze them out. The liquid will squeeze them out, and the little bubbles of gas that accidentally form get squeezed out. And so there is a kind of symmetry between these. On one side, you have gas with little droplets of liquid. On the other side, you have liquid with little bubbles of gas. But as you said, as you move around here, the little droplets of liquid begin to become more prominent. They grow, they are more numerous and maybe bigger, and the gaseous phase sort of smoothly goes over to the liquid phase. But right along here, you have sort of both liquid and gas at the same time. You have little lumps of liquid, little lumps of gas, and so forth. Just in the same way that if you looked at the magnet through a microscope, you would discover islands of downspin and islands of upspin, equally numerous along here. Down here, you would find more islands of downspin. Up here, you would form more islands of upspin. Right on here, you would find an equal population, and you would go smoothly from one to the other. Quite different what happens when you go across here. When you go across here, you'll see mostly gas or mostly downspins until you get right to here, and then you jump to mostly upspins.
In the case of the magnet, the y-axis is the magnetic field.
The external magnetic field. Yeah.
Right. And in the case of the liquid and gas, what is the y-axis?
The y-axis is the chemical potential. Remember what the chemical potential is it's just a device for increasing the density. It's a device for increasing the density. The bigger or smaller you make depends on your definition, but pushing the chemical potential one way or the other tends to make it more or less dense. Increase. Do you remember what the chemical potential was? It was a Lagrange.
You don't remember? I don't think you covered it in this class. You
Oh, I didn't?
covered it in graduate.
Oh, I didn't explain what the chemical potential is. Oh, okay, why don't I do that right now? Okay, good. My apologies. Let's talk about chemical potential. All right, chemical potential is a tool for problems. Let me erase the blackboard. All right, let's imagine we go back to the very beginning where we have a bunch of identical boxes. And remember what the game was. We allowed energy to be interchanged between the boxes by a weak interaction, which allowed the boxes to exchange energy between them. And then what we calculated was the probability distribution for a given box given a total amount of energy. In the situation in equilibrium, where they come to equilibrium and when energy is going back and forth at equal rates, so it's at equilibrium, then there's some total energy, and given the total energy, we can calculate the probability distribution for a given box to have a... Now, when we did that, we introduced the temperature or the inverse temperature as a Lagrange multiplier. We said we want to maximize the entropy subject to a constraint. And what was the constraint? The constraint was that the total amount of energy was fixed. So we said, let's maximize entropy given that, that E1 plus E2 plus E3, blah, 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 blah. No, that's not right. That's not what I want to write. I want to write that the number of boxes with energy E1 plus the number of boxes with energy E2 and so forth all add up to the total energy of the system. E total. The number of boxes with energy E1, the total energy that they have is N times E1, so let's call that N1, N2, and so forth. Just go back to your early notes. I just want to remind you. And how did we implement this constraint? This was a constraint. We had a problem of minimizing or maximizing something. We wanted to maximize the entropy. I'm not going to go through it. We wanted to maximize the entropy given that the total energy is fixed. The way to do that was to introduce a Lagrange multiplier. We introduced the Lagrange multiplier. I can't remember now if it had a plus sign or a minus sign, but we call that Lagrange multiplier beta. And that beta multiplied some n sub I e sub I. Or, well, that's good enough. That's what we did. We went through this. We maximized the entropy. And what do we find? We found that the probability distribution for a given box was e to the minus beta times the energy. And if we want to normalize it, we had to put 1 over the partition function there. Now that's just back to first lecture or second lecture or whatever it was. Now supposing that it is also possible not just for energy to be exchanged between these boxes, but particles to be exchanged. Helium atoms, if this was helium, for example, or whatever it happens to be, or water molecules if it's water. In other words, there's little thin pipes here. Little thin pipes, and those little thin pipes allow water or fluid to be exchanged back and forth. Then we will not know with absolute certainty what the number of particles in each box was. Remember that we've assumed previously that each box had a given number of particles, but now we don't know what the number of particles is in the box. It also has a probability distribution. It also has a probability distribution, but here now is what we will have to do. We will have to add 2 Lagrange multipliers. We'll have to The one Lagrange multiplier is for the total energy. And so that's summation of n sub I, E sub I. Incidentally, the n sub i's, if you remember, were proportional to the probability. What was I in this formula? Anybody remember?
For the,
Dimension in
which
space,
box? Which box?
No, not which box. Not which box. Okay, let me, I'll remind you because you probably have forgotten by now, so have I. Okay, what n sub I and E sub I were, each box can be in any one of a whole bunch of states. Here are all the states. Energy, here's the first state, the second state, the third state, the fourth state, and so forth. The states are labeled by I. N sub I is the number of boxes that occupy the ith state, or the number of boxes in which you will find the system in the ith state. N sub I times the energy at the ith state, if I sum it over all I, that gives me the total energy. It's the number of boxes in the first state times the energy of the first state plus the number of boxes in the second state times the energy of the second state, and so forth and so on. This has to equal the total energy. That's the first thing. Now, do you remember if there were n boxes here, do you remember the formula that n sub I over total n is equal to the probability of the ith state? In other words, the probability that any given box is in the ith state is just proportional to the fraction of total number of boxes that are occupying the ith state. And we call that the probability. So we could divide this formula, I'll just go through it with you again. We could divide this formula by n, E total divided by n. What's E total divided by n? It's the average energy in any given box. So we'll just call this E, the average energy in a particular box. And this becomes summation over I, P of I, EI equals the energy. This was a constraint. This was a constraint, and what we want to do is to maximize the entropy. Maximize the entropy. Remember what S is? What's S? Minus summation over I, P of I, log P of I. That was the entropy, and we want to maximize it subject to a constraint, and the way you do that is to introduce a Lagrange multiplier beta. Forget this over here. Introduce a Lagrange multiplier beta, and then maximize this expression with respect to pi. The pi's are the variables. We're trying to find out what the probability of the ith state is. We want to maximize the entropy subject to the constraint of a given energy, and if you remember, we went through it, it gave us that pi is equal to what? E to the minus beta E sub I divided by z. Z is just there to make the total probability add up to 1. Right? That's the probability of being in the ith state. Now we've done something new. We've allowed particles to jump back and forth. We've allowed particles to jump back and forth, but the total number of particles is not allowed to change. The total number of particles we'll assume is conserved. The total number of helium atoms or water molecules or whatever it is conserved, and so we can write another constraint. The other constraint is that the number of particles in the first box, let's see, the number of particles in the first box in 1 plus the number of particles in the second box plus the number of particles in the third box and so forth, not plus, all have to add up to the total number of particles. N1, N2, and N3 and so forth, they can change, but the total number of particles has to remain constant. Yeah?
I just want to, when you did this first time, you had two constraints.
Yes, 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 there was yeah, that wasn't the number of particles, it was the number of boxes, right. Yeah, you're right. There actually were two constraints. The total number of boxes added up to n, but that's right. All right. I had hoped to get around that. It's there. All right, so there's another Lagrange multiplier that has to be added, and that Lagrange multiplier, instead of multiplying the energy, multiplies the number of particles in each box. I'll tell you what the net result is. The net result is, we can now think of the probability as a joint probability that the system is in the ith state and it has n particles. It's not just a question now of which quantum state the system is, but also how many particles it has in it. Right? So there's a probability which is a function of the number of particles in the box and also which of the many quantum states the box is in for that many particles. And the answer that you get by the same exact analysis is another term up in here, which is minus beta mu times the number of particles in the box. This beta times mu is a somewhat artificial decomposition. You could have just called beta and mu the original Lagrange multiplier. It's beta times mu, which is the Lagrange multiplier. It's just a historical definition that, that this wasn't called a single thing, beta times mu, but that's the way it is. That's the way it is. All right. What does mu do for you? What does tuning mu do for you? Well, first of all, mu is very much like a temperature, or beta times mu. This combination here is like a temperature, but what does temperature do for you? Forget this. What is temperature? What does changing temperature do? It allows you to tune the energy. Right? By changing the temperature, if you know you have a given amount of energy, the way you would deal with this is you would change beta until the average energy is equal to the average energy that you think is in the box. So beta is the tuning device. The temperature is the tuning device, the knob that you change to change the energy in the box. Mu is the knob that you change to change the number of particles in the box. Right? Mu is the knob that you change if you want to change the number of particles in the box. And why is that? Well, you can see if the probability, let's forget this factor over here, if the probability goes as e to the minus beta mu times n, then the average number of particles in the box is going to be controlled by this mu here. Let's see, the smaller mu is, the more particles will be in the box, or whatever it is. So chemical potential is just a device for tuning the number of particles in a box in a situation where the number of particles in the box can fluctuate or change in one way or another. All right, I didn't want to spend a lot of time on that, but let's come back to here now. How do you change mathematically, in terms of the statistical mechanical partition function, how do you change, oh, incidentally, the partition function z, let's think about the partition function z. The partition function z satisfies z is equal to the sum over all of the states of the system and the number of particles in the box, number of particles in the box and the various states that the particles can be in, of e to the minus beta e sub I minus beta mu times the number of particles in the box. That's just to make sure that the total probability adds up to 1. So that's z. And notice it has a new thing in it. It has a thing which allows you to control the number of particles, called a chemical.
Is the capital N in that formula supposed to be N sub I?
No.
No.
It's the number of particles in the average number of particles in all the boxes. That's right. The average number of particles in all the boxes. All right, so this is a device, and how do you choose mu? You choose mu by calculating the average number of particles from this probability distribution, and then set it equal to what you think the average number of particles is, whatever it happens to be. By changing mu, yeah.
Isn't n the possible number of particles in the box? Because n can be anywhere.
In this formula, it's the possible number of particles in the box.
Anything from 0 to...
That's right, and you sum over it. But you can also use this now to calculate the average number of particles. How would you calculate the average number? You take the probability distribution, multiply it by n, and sum. So you also have a formula for the average number of particles in the box. Right. So if you know there are altogether n total particles altogether divided up among all the boxes, then you think you know how many particles should be in each box. You simply tune mu until you get that many particles. Yeah. But obviously, tuning the number of particles in a given box of a given size is the same as changing the density. You can think about how to do that. You just divide by the volume. And so the chemical potential is a trick in the partition function for changing the density of the gas. What is that? Mu is the chemical potential. And I have a strong feeling that my definition of mu differs from everybody else's on Earth by a sign. I discovered that sign the other day. I've been going out through my entire life with the chemical potential having the sign that I've given it here. I'm not going to try to correct it now. Whatever it is the thing which allows you to vary the density. Now, what is the density in this lattice fluid? The density in the lattice fluid is, roughly speaking, the number of upspins divided by the volume. Capital N becomes the number of upspins here. A downspin is empty, an upspin represents a molecule. So capital N is just the number of upspins. How do you change the number of upspins? How do you tune the system from essentially no upspins and bias it towards lots of upspins? You change H. When H is down, it pushes all the spins down. No matter what the temperature is, if H is down, it will bias the system toward few upspins. And if you want to change the density of upspins, what you do is move along this H-axis. So the H-axis is closely connected. It's essentially the same as the chemical potential. And it's the thing that you tune to change the density of the gas, the density of the fluid. Yeah.
A quick question, terminology is, you have one Lagrange multiplier beta, and the other Lagrange multiplier is beta mu?
Well, yeah, it's a historical fact. We could have just called it lambda.
Okay, so it's different than beta.
It's different than beta, and historically, lambda was set equal to beta times mu.
It's a little confusing there.
Yeah, I know. Right. We could have just called it lambda, but that wouldn't be. That would be ahistorical, and it would be different than the standard terminology. So the standard terminology is to replace lambda by beta mu. But think of beta mu as itself a quantity. Incidentally, you calculate the average number of particles by differentiating the logarithm of the partition function with respect to mu. Differentiating with respect to mu, well, differentiating with respect to beta mu, brings down an n and allows you to calculate the average number of particles. So you calculate the derivative of the logarithm of the partition function with respect to beta mu, and that gives you the mean number of particles, which is very similar to how we calculated the mean energy, differentiate the log of the partition function with respect to beta. Similar idea. Okay, that is the basic setup for, yeah.
How does an experimentalist measure the chemical potential? I know how they do temperature, but how do you?
Well, I'm not sure you do measure the chemical potential. Yeah. How do you measure the chemical potential? I would say you measure the density more likely than the chemical potential. I don't know, I never think about measuring the chemical potential. I think of it as a tunable parameter that changes the density, and that the density is the thing that you... Yeah, it is the amount of energy that it takes to remove a system from a box. Yeah, it is related to the work function. Yeah, how much energy it takes to remove a particle from a box. Yeah, it's true. Okay, so good. But now I want to talk about something very exotic, extremely interesting, and took many years to really get right. It has had an enormous influence on statistical mechanics and quantum field theory. I doubt that that's obvious to anybody in the room what all of this has to do with quantum field theory, but let's not worry about that. It has to do with the behavior of the system as you approach the critical point, let's say moving along h equals 0. We don't even need h for this here. We just move along from the high temperature side, getting closer and closer to the critical point. What is it that happens at the critical point? And something very interesting happens at the critical point. The first idea that you need in order to understand the critical point is the idea of a correlation length. We talked, I think we talked, did we talk at all about the correlation function? No, we didn't. So I'll tell you what the correlation function is. We don't need to talk about how you calculate it. It's an average. It's an average of the product of spins at two different points. Let's say sigma of A and sigma of B. It's the average value of the product of sigma A and sigma B. It measures the degree of correlation between the spin at point A and the spin at point B. These could be 2 points on the lattice. They could be near each other. They could be far from each other. What happens if A is equal to B, incidentally? Sigma squared is just equal to 1. So the correlation function at the origin, let's call it, in other words, when A and B are the same point, that's always equal to 1. But now let's separate the points. Okay? All right, so how do I calculate the correlation function at these two different points? And let's go to extremely high temperatures. Let's start at the high temperature end of things. All right? Not at the magnetized phase, but at the high temperature end. Infinite temperature, enormously high temperature. And what happens at very high temperature? They're jiggling around like mad, and the temperature is so high that the bonds are not very potent at holding the spins aligned with each other. Right? So let's talk about the correlation or the average of the product of two spins neighboring to each other at very, very high temperature. What would you expect that it would be? 0. 0, because even if you freeze, you can think of it this way. You can think of calculating it by freezing this spin up and then calculating in the presence of this spin up, calculating the average of this spin. And then that's the way you can think about it. It really represents the probability that if this spin is up, then this spin is also up or also down. Some average, given that this one is up, what's the probability that this one is up or down? And that represents, that's the correlation function. Or better yet, given that this one is up, what's the average of this one? All right. So what would you expect again at very high temperatures? Just 0, because they're fluctuating completely independently, because the temperature is so high that the bond joining these is ineffective. What happens as you start to lower the temperature? As you start to lower the temperature, if this spin is up, it will bias this spin to also be up, because the energy will be lowered if they're parallel. If the spin is down, it will also bias it. So what starts to happen is that sigma times sigma starts to not be 0 anymore, and in fact is usually positive. It's positive because if this spin is up, this one is more likely to be up, so sigma times sigma is positive. If this spin is down, then this one is also more likely to be down, and so again, sigma times sigma is positive. And so this correlation function between neighboring points at moderately high temperatures will stop being 0 and be small but non-zero. What about the correlation function between second nearest neighbors?
Square? Square the one?
It'll be more or less, that's right, it'll be more or less the square of the correlation between first nearest neighbors. That's right. That in fact is about what it is. Okay. What about you go way, way down the line here? And there's nothing that's special about moving along the horizontal axis here. We can move vertical axis, or we can move at a 45 degree, but what would you expect as you move way down here? Again, you'll expect each time you move, you'll lose some correlation. And in fact, you lose the same fraction of correlation, roughly speaking, and that means that this is going to be exponential in the distance between these points. If each time you lost, let's say, half the correlation, if the correlation between nearest neighbors was a half, and second nearest neighbors was a quarter, third nearest neighbors was an eighth, and so forth, you might expect that this would behave like e to the minus some parameter m times the distance between them. Let's call the distance between them d. Distance means number of lattice sites between them. So when you're very, very far away, the correlation is extremely weak, exponentially weak. When you're close by, the correlation function is stronger. The correlation is stronger. This m depends on the temperature. At very, very high temperatures, the correlation falls very rapidly to 0. Let's imagine plotting it at different temperatures. Correlation function is always 1 at d equals 0, so this is d. At extremely high temperatures, the correlation function just drops like a bomb down to 0, and so by the time you get over to the first lattice point, it's negligible, small at very high temperatures. And then it just stays small. Gets even smaller, 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 exponentially. What happens as you lower the temperature? As you lower the temperature, the correlation function continues to drop as an exponential, but the rate in here at which it falls becomes more and more gradual. As the temperature gets lower, the rate at which it falls becomes more gradual. And that means that m is a function of temperature. M is a function of temperature. And what does it represent? It represents the distance that you have to go out in order that the correlation has dropped by a factor of e. Right? How far do you have to go out in order that the correlation function is dropped by a factor of e? That's what m represents. It's also called the inverse correlation length. The inverse correlation length. The correlation length is the width of this curve. Here, the correlation length is very, very small, and m is very large. As you lower the temperature, the correlation length gets longer and longer, and the inverse correlation function gets smaller and smaller. Okay? When m is very small, this function very gradually goes to 0. Okay? So m is a function of t. It represents the inverse of the correlation length being the distance out to which you have to go in order that you've lost a factor of e in the correlation. And those are a set of definitions, but they're clearly a useful set of definitions. And what the correlation length tells you is it just tells you exactly what it says. How far out on the lattice will you feel the effect of nailing one particular spin in place? Supposing you nailed one particular spin in place, given either up or down, how far away is it felt? That's called the correlation length, and it's inverse to this m of t. So m of t decreases, obviously decreases with temperature. correlation length increases, M of t decreases. Yeah.
In all these cases, you're assuming there's nothing between the two test points, right?
Yeah, I am.
So you're making an assumption about the density in there implicitly. That you're making an assumption that it's not so dense that you're squeezing
Dense in the sense of...
particles on every lattice point.
Say again?
Dense in the sense of particles on every lattice point.
Oh, there could be a particle on every lattice point. Then the correlation could be.
So it's just a superposition? It's just a superposition of all the effects then?
Yeah, but at very high temperatures, with no chemical potential, you will not find that there's a particle on every point. You'll find it's about half filled. Half filled at high temperatures. Half filled, half empty.
Doesn't that depend on how finely you draw the lattice?
How finely you draw the lattice? Yeah. No. No, no. Nothing depends on how I draw the lattice. Drawing the lattice is just, I can draw it on a piece of paper, I can draw it on the blackboard, I can draw it on the ceiling, same system.
The spin could be up or down, so at each point in the lattice, the spin could be up or down, so half of them are up and half.
Right, half of them are up and half of them are down at high temperatures typically. Yeah, okay, good. But the interesting thing is this correlation length gets longer and longer. Okay? Now, imagine you now pass below the critical point. What happens to the correlation function below the critical point? Let's think about that. Take sigma of A times sigma of B below the critical point, and below the critical point, here we are below the critical point, we could be here or we could be here. Below the critical point, the bias of just one spin being up is enough to bias. Remember what happens at below the critical point. There's this sort of instability that the tiniest little perturbation, which biases it one way or the other, will lock all the spins, not all the spins exactly into the same direction, but will bias all the spins so that the average magnetization is in one of the two directions. So supposing we freeze sigma A to be up, and now we look at sigma B. Well, the sample has been biased by sigma A, and we're in the magnetized phase, we're below the critical temperature, and so what's going to happen is sigma B will, on the average, be in the same direction as sigma A, but right out to infinity. Right out to infinity. In this magnetized phase here, one spin pointing up is enough to tell all the others that on the average they will point up. That's what happens to this down below the critical temperature. So what we can say then is that sigma A, sigma B will go to some constant, some positive number, I don't know what to call it, let's just call it a number, constant. As you move further and further away, sigma A, sigma B will go to some constant. That constant will also depend on the temperature. If you're at very low temperatures, the spins will tend to align each other rather rigidly. If you're at zero temperature, the only two possibilities are all spins up and all spins down. What happens to this at zero temperature? It's 1. If sigma A is up, then sigma B is up. If sigma A is down, then sigma B is down. So at zero temperature, let's approach now. I'm going to use red to approach from the low temperature side. This is what happened from the high temperature side, and this always goes to 0 as long as the temperature is high enough. But now, here's temperature 0. What happens at a little bit higher temperature? You're still in the magnetized phase, and you still go to a constant out here, but a little bit less constant. Things are not rigidly held in place as well. Eventually, you come down to the critical temperature. And as you get to the critical temperature, that's the temperature which divides these two behaviors. What's the behavior here? Exponentially decreasing correlation. What's the behavior here? The correlation function doesn't decrease. What divides them? What divides them is the critical behavior. Let's see, I have trouble drawing it. The critical behavior, which is neither constant at infinity, nor is it exponentially falling. Every one of these eventually falls exponentially. Every one of them falls exponentially. What about this critical one here? What's in between being constant and falling exponentially? Well, there's a lot of things, but... Hyperbolic means what? 1 over x. Well, how about just 1 over x to a power? 1 over d to a power. At infinity, it's 0. Yeah, this falls and falls and falls and falls, but it never falls as fast as an exponential, and it fails to have a finite limit at the end. All right. So what is known, this requires a proof and it requires some work, but what's known is right at the critical point, right at that critical point, this just falls off as a power law. This falls off gradually as a power law, not as an exponential. That's the characteristic critical behavior, that the correlations are long range, sort of 1 over r to a power. For the two-dimensional Ising model, it's 1 over distance to the 1/8. So it gradually falls off. The number is not terribly important. Okay, so that's one of the things that happens at that critical point. Now, as you approach the critical point, imagine that you looked microscopically at the magnet. The correlation length here, the fact that it has some size, what it's really telling you is that the magnet is filled up with blobs of spins, bubbles of spins, more or less pointing in the same direction. There are blobs of spins up, there are blobs down, but they're not exactly all up. They're somewhat biased toward up, they're somewhat biased toward down over here, somewhat biased toward up, down, a kind of patchwork where the patches tend to be about as big as the correlation length. If you take 2 points beyond the correlation length, out way past the correlation length, there isn't much correlation between them. Something over here is as likely to be up or down if this is up. But if your 2 points are within one of these blobs, then most likely they're pointing the same direction. All right, so it's this blob, it's this formation of these bubbles or blobs of material. Could be, it's really, what is it? It's liquid gas in the case of the fluid, or upspins and downspins in the case of the magnet. These structures more or less follow in size the correlation length. So this m of t is basically just the inverse of the size of the blobs that you would see if you looked carefully.
Size 1 over m?
Yeah, size 1 over m. Right. And as you get closer and closer to the critical point, what happens to m is it goes to 0. M goes to 0. It's no longer a exponential, but gives way to a power law, and that corresponds to m going to 0. All right? Or the correlation length blowing up. The correlation length gets bigger and bigger blobs like this. Okay? So that's what. Now what happens? Of course, I should say this, that each one of these blobs is not a pure phase. It is not pure all spins up. This one is not all spins down. This one just has a preference for ups. This one has a mild preference for downs. What happens as you get closer and closer to the critical point, two things happen. First of all, these blobs get bigger and bigger. But second of all, they tend to fade. Fade means what's the word when you put your nice colored shirt with lots of contrast through the washing machine too many times? Well, fade. Fade. If you were to look at this as you move closer and closer to the critical point, what you would see is these blobs blowing up. Okay. Now, you could say, all right, let me just try to restore some, just for convenience, let me squeeze the whole thing down so that the blobs have the same size. I'll have to make the lattice smaller. All right? I'm just going to do that. I'm going to do it as I move closer and closer to the critical point. The blobs indeed get bigger and bigger, but just as a matter of convenience, so that I don't have to draw the whole thing on a blackboard which is 20 miles long, what I'll do instead is rescale the whole diagram so that the blobs remain the same size. The blobs remain the same size. Moreover, there are blobs within blobs. There are blobs within blobs within blobs. But the net effect in the biggest blobs is to be, on the average, upspin. In the biggest blobs of the downspin type, the net effect is to be downspin. So that's what the correlation length is. But what happens to these blobs, even if you plot them always in such a way that their size looks the same, this is just an arbitrary rescaling of the lattice, just so that we can redraw it, so that I don't have to run out of the room to the next room out there to get closer and closer to the critical point. Instead, we imagine in our heads making the lattice spacing much smaller so that the blobs occupy more and more lattice spacings. Okay? But in addition to the blobs getting bigger, they get fainter. They get, what's the right word? Bleached, I think somebody said. Faded. Faded like putting your polka dot black and white shirt through the dishwasher, not the dishwasher, the washing machine too many times. And what will happen? After a while, the contrast between the up blobs and the down blobs will get weaker and weaker and weaker. That's what happens at the critical point. In fact, at the critical point, you have blobs of every size, right at the critical point. When the biggest blobs grow to infinity, there are still smaller blobs. The biggest blobs grow to infinity, but are infinitely faded. The next biggest blobs, they're still there. They're pretty big. They're not quite as faded. Smaller blobs within blobs, not quite as faded as their predecessors, and smaller. What happens at the critical point is a kind of self-similar fractal structure. A self-similar fractal structure that on every scale, if you look at it, you see the same thing, namely blobs within blobs within blobs, but as you look on smaller and smaller scales, the contrast, the density contrast gets stronger and stronger. If at the same time that you rescale the lattice, push the temperature closer to the critical point, push the temperature closer to the critical point, rescale the lattice, and also rescale the density, the contrast. The contrast, you have your television and you turn down the contrast or turn up the contrast. As you look at smaller and smaller blobs, if you turn down the contrast, then you literally see the same thing at every scale. The only distinction between what you see at one scale and another scale is the intensity of the contrast between the blobs. If you allow for that, if you allow for the decrease or the fading of the contrast from as you get closer and closer to the critical point, then what you see is just a self-similar fractal which looks the same on every scale. Everybody know what I mean by self-similar? It just means it looks the same at every scale. You could not tell by looking at it through a microscope, unless your microscope, of course, was strong enough to see the actual lattice structure. I'm assuming we have a microscope which can't see the actual lattice structure, but it sees blobs. Then you, at the critical point, you cannot tell, or close to the critical point, you cannot tell how big the, well, you can't tell which blobs you're looking at. They all look the same, except for the strength of the density contrast. The smaller they are, the stronger the density contrast. In fact, if you get down to the lattice spacing itself, you will see upspins and downspins. Upspins are absolutely black, downspins are absolutely white, and so you'll see spins next to each other, slightly biased maybe, but with very strong contrast. On the other hand, these very big lumps here, those very big lumps will have weak contrast. In fact, the fact that the contrast gets more and more faded is just the fact that this correlation function gets smaller and smaller as the distance between things gets big. As the distance between points gets big, right at the critical point, there are blobs of every size. But if you take 2 points, the correlation will mainly be due to blobs of about the scale between the 2 points. What is it that will lead to a correlation between these 2 points? The likelihood that there's a blob about that big. The further apart you take them, you'll be sampling bigger and bigger blobs, but bigger and bigger blobs have less contrast, and that's why the correlation function falls and goes to 0, because for very, very big blobs, the contrast has faded. You can actually see this in simulations of magnetic systems. You look at the simulations and you see, patterns of blobs and blobs and blobs inside blobs. It's hard to really see anything. More or less you see white noise or black noise or whatever. But if you look carefully, you can see some slightly over-dense regions, some slightly under-dense regions. And then as you tune the system toward the critical point, the over-dense regions and the under-dense regions grow. And you'll also see that they have blobs inside them, which are even more over-dense, and blobs inside blobs inside blobs. And so this pattern of self-similarity is the first thing that happens at the critical point. Something else happens at the critical point. If you look at these blobs, the theory of these blobs, the actual crystal, the actual lattice itself was not very symmetric. Certainly did not have circular symmetry. Right? It has just square symmetry. It's a square lattice, for example, and so it's not isotropic. It's by no means isotropic, and you would not expect the properties of the magnet to look isotropic. You wouldn't expect the correlation function to be truly isotropic. You would expect it to be different along the axes than it is along the 45-degree angles. But as you get closer and closer to the critical point, the system loses memory of the basic underlying lattice theory, and it just gets more and more rotationally symmetric, more and more isotropic, until right at the critical point, by looking at these big, big blobs, you cannot tell which direction the lattice is oriented. So that's another thing that happens, a washout of the basic starting point, if you like. The basic starting point being some specific lattice with a given orientation. I'll give you another example. We might have made a more complicated structure. Instead of the magnet having only nearest neighbor coupling, we might have had a lattice with nearest neighbor and second nearest neighbor coupling, or neighboring couplings, this spin times this spin, but maybe also diagonal couplings, spins, energy of the spins depending on diagonal couplings, and maybe second nearest neighbor couplings and so forth. We might have invented a more complicated model sigma times sigma nearest neighbor plus sigma times next nearest neighbor, and so forth. Let's suppose that all the bonds favor parallel spins. Let's suppose that it tends to favor parallel spins. Then there are detailed differences between a magnet with second nearest neighbor couplings and first nearest neighbor couplings. They're in detail different. The details of the thermodynamics are different. And in particular, they're quite different at high temperatures where the correlation length is very small. In general, the details of the lattice and the details of the structure will be remembered at the high temperature limit. But as you lower the temperature and these blobs get bigger and bigger, the system starts to forget what the details were. So the critical behavior of the second nearest neighbor coupled lattice is exactly the same as the critical behavior of the first nearest neighbor coupled lattice. The diagonal bonds don't do very much. They may shift. What they will do is they will shift the critical temperature a little bit. The effect of changing the bonds and the nature of the microscopic interaction between molecules, it will have the effect in general that it may change the critical temperature a little bit. But whatever the critical temperature is, as you approach it, whatever it is, you'll always see exactly the same pattern of fractal, self-similar type of structure, which will forget the details of the lattice. That's the nature of critical behavior. Bubbles or blobs at every length scale, stronger ones at small length scale, more faded ones at large length scale, contrast going down and down and down. There's an interesting experimental consequence of this. Has anybody ever seen critical opalescence? Critical opalescence is a wonderful phenomenon. If you take a liquid, helium is a good example, but any transparent liquid, and you tune its temperature toward the critical point. You tune temperature and density, move along here, getting closer and closer to the critical point. What happens is exactly this. Blobs of every length scale form, of every length scale, and the effect is that it scatters light. Light passing through it will be scattered at every wavelength. Every wavelength will be scattered pretty much the same way as every other wavelength. If you're away from the critical point, the largest blobs will have some given size, and wavelengths longer than that will not be scattered. Okay? But as you tune toward the critical point, longer and longer wavelengths will be scattered, and light passing through a material close to its critical point, it's called critical opalescence. You can imagine what that means. It means, how would you describe opalescence? Well, all colors, it gets very milky.
You have a filter. You have a filter, basically.
You have a
filter.
Filter.
A filter.
A filter. Well, you have a filter, but the point is that it scatters light. It scatters light that if you're close to the critical point, but not that close, you'll scatter all wavelengths down to microwaves. Get closer to the critical point, and you'll start scattering radio waves. I'm being a little bit extreme, but at first you scatter optical light, then you scatter optical light and infrared, then you start scattering optical light, infrared, and microwaves, then you start scattering everything. And the whole thing just looks like a milky opalescent material. It loses its transparency because it just scatters at every wavelength. So that's called critical opalescence, and it's a real phenomenon. I wish I could show it to you here, but I don't have any liquid helium. I think liquid helium is probably the best.
Is this approaching the critical mass by cooling to it, or by cooling or by heating?
It doesn't matter really, but I think it's best to do it by cooling. Yeah, normally it would be done by cooling. You would start above the critical temperature and slowly cool down to the critical temperature. And as you cool down, you'll discover the thing becomes a better and better scatterer of light. It doesn't really absorb the light. It just becomes Not opaque. There's another word. What's in between opaque and transparent? Translucent. It becomes translucent, but translucent at every wavelength.
Would that be because of the different refractive index between the solid, and, I mean, the liquid and the refractive index changes?
Yeah. There's a difference between the index of refraction and the liquid and the, and so it scatters the light. Yes, and at all scales. There are structures there at all scales that scatter the light. Right, exactly. And in fact, one word that's used to describe this self-similarity is it's called scale invariance. Scale invariance means the phenomena of things looking the same at every scale. But as a rule, you have to keep in mind that the contrasts tend to fade, and so you have to artificially jack up as you look at the bigger and bigger things. You have to artificially renormalize, is the word, renormalize the density contrast so as to keep it the same. Then what you see at every length scale is the same.
Quick question about the fading.
Yeah.
I'm trying to understand it. So if you have 100 molecules or whatever, if like the ratio is like 97 or spin up and 3 spin down, that's very contrasty. If it's 85-15, that's more faded.
Right.
Wouldn't that be just the entropy of?
It is certainly connected to entropy, but the fact that this correlation function falls at large distances like a power law tells you that the intensity of the contrast within a blob of a big blob is less than the intensity of the contrast of a smaller blob. So that's exactly what this falling correlation function tells you. So it's a pretty interesting phenomenon, and more than interesting, it's sort of at the root of how quantum field theory works, but we haven't talked about quantum field theory. And it is the ingredient in many approximate schemes. In many approximate schemes, you take a system which you expect at the end to be isotropic and homogeneous. You're really talking about some isotropic, homogeneous thing. A quantum field theory would be a case in point where things are rotationally symmetric, translationally symmetric, and so forth, and you want to model it. You want to model it as a system on a lattice. Why? Because it's convenient to replace the continuous distribution of field variables that fill space by an approximate version of the theory where all the degrees of freedom live on individual lattice sites. Right? What's going to happen? Well, you're going to wind up with a description where the lattice behavior will stick through and get in your way. The system will not look translationally invariant because the lattice is not translationally invariant. There will be corners to things because the lattice has corners. But how do you restore in such a system the behavior that you were looking for in the first place, which was this smooth, translationally invariant, rotationally invariant behavior? And the answer is you tune yourself to a critical point. Whatever the example is, whether it's statistical mechanics or quantum field theory, you tune the parameters until you get to a point where the correlation length is much, much longer than the lattice length. And that limit, the artifacts, the lattice artifacts disappear. So this is a common tool in quantum field theory and in statistical mechanics and so forth. Okay, so let's see, where are we? Any questions? Yeah.
I got one. Is this related to superconductivity in any way?
Not particularly. Not particularly. This is called, incidentally, the rescaling that I've described here, this rescaling and constantly pushing the blobs back to the same size. That's called renormalization group. It's got to do with renormalization in quantum field theory. Does it have to do? Well, yes and no. In some systems, there is a phase transition in a superfluid or in a superconductor which behaves exactly this way. Yeah, but it's not really got much to do with the phenomena of superconductivity itself.
Are there applications of this to cosmology, like the microwave background radiation?
Yes, yes. Yes, there are. Right, that's a good point. The fluctuations that are seen in the sky, the microwave background is very homogeneous, of course, extremely homogeneous or isotropic across the sky. But if you look at the level of 10 to the minus 5, you see over densities and under densities and so forth. In other words, you see blobs. You see a blobbiness. And in fact, you see the same blobbiness at every scale. You see exactly the same sort of self-similar, scale invariant kind of behavior as at a critical point. Now, is it connected with critical points? Yes, it is, but not in a completely obvious way. But it is. It looks very much what is seen in the sky when you look at the microwave background and you see these maps of the microwave background and so forth, is self-similar in the same way that the critical point, self-similar or scale invariant. Scale invariant is the word that's used. So it's almost as though the early universe was generated from a Monte Carlo simulation. Monte Carlo just means a statistical averaging of a magnetic system, but that's not the real reason for it. The real reason for it is quite different. The organization in the sky did not come from a second order phase transition. Incidentally, jumping across here, where you have a real jump in the density, that's called a first order phase transition. The order of the transition, the lowest order transition corresponds to the biggest, most abrupt jump. Right? So a first order phase transition is one in which density or magnetic field or whatever the appropriate variable is, the obvious variable, makes a discontinuous jump. If you approach along here, along the temperature axis with no bias, you come right down to this critical point over here, and then if you go a little bit further, you'll see spontaneous magnetization. Here you don't see anything discontinuous. Right at this point over here, the magnetization is 0. And as you move in, the magnetization, the magnitude of the magnetization continuously increases. So there's no sudden jump in the magnetization here. It's just 0, 0, 0, 0, 0, 0, and then it starts increasing from here, but smoothly. That's called a second order phase transition, when the density or magnetization is absolutely 0 until a critical point and then starts to increase smoothly from there. Something is discontinuous over at this point over here. If you differentiate the magnetization enough times, you will find that there's some singularity in it. But it's a more subtle effect. Second order phase transitions are more subtle, and third order phase transitions are even more subtle and almost never happen because they're so subtle. Okay, yeah. I can't think of one offhand. I once knew one. I don't remember what it was. But they're rare. And offhand, I cannot remember what system had a third order phase transition.
The chemical opalescence phenomenon, is that what happens?
Critical opalescence.
Critical opalescence. Is that what's happening when water vapor condenses into clouds?
Well, I don't think no. No, it's not. It sort of looks like it, but it's not. The critical point, anybody know what the critical temperature of water is? Something like that. I don't remember exactly, but it's way, way above boiling.
It's about 300. 306 or something. 306?
360 degrees, something like that? So yeah, 306 degrees. Right. So this temperature here is at 306 degrees and some pressure. Some pressure and some temperature, or some density and some temperature. Some density and some temperature, there's a critical point, and that critical point is the second order phase transition. And if you want to see it, you've got to, in water, you have to be up at 306 degrees. On the other hand, in helium, it happens at a very low temperature, a much lower temperature. And so you can see liquid helium boiling into helium vapor. And if you bring the helium to just the right density and temperature, you can see the critical opalescence.
Okay. When, in the cosmology example, if you look at over time when the dark energy thing took over from the matter, could that be considered like a critical point as well?
No.
Phase transition?
No, no, that's not a critical point, any kind of critical fact. In cosmology, the main analog of this kind of critical behavior is what's called the scale invariant fluctuation spectrum. The spectrum of fluctuations and perturbations over densities and under densities that were there at primordial times before galaxies formed, just the surface of last scattering. Surface of last scattering, if you look out on the sky, looks like this kind of behavior. And I mean quantitatively it looks scale invariant. Now, it's actually not completely true because the system gets processed a little bit. I mean, it's quite obvious that gravity took over and started manipulating the overdense and the underdense regions. But if we could have seen what that sky was like before gravity started to work on these overdense and the real primordial fluctuation spectrum, it would look very much like the critical point of this magnet.
On inflation, I hear when you go from the, I guess, the vacuum on steroids, the really high one, down to the regular one. And I've heard that they had some original problem with the theory.
It's called reheating. That's called reheating. Yeah, why reheating and not just heating?
They said, and it didn't make any sense to me then, but they said it was originally modeled as a first order phase transition.
Okay, yeah. Right, we can talk about that next time a little bit. Remind me. Yes, it was originally modeled as a first order phase transition. That was a disaster. And I can tell you why. We have enough things I can tell you why, but I'm not going to tell you why now. I'm fading. My contrast is diminishing.
For more, please visit us at stanford.edu.